Welcome to 1.6 or inverse functions, and before we get into the terminology and the definitions of inverse functions, I want to show you my interpretation of an inverse function. And if you've been watching the videos up to this point, as you know, I often refer to the x-axis in terms of time, let's say days, and the y-axis in terms of height, let's say inches. So if I put in an x value, I'm putting in a days, well, that turns that into a y value or a height. And let's say I have another function where I could take that value, let's call it g, and if I could run that value that came out of f through g and return to x, in other words, g of f of x, if that equals x, then g and f are inverse functions. Basically, if we have a second function that undoes what a first function does, they are inverses. So let's take a look at the definition. Let f and g be two functions such that f of g of x equals x for every x in the domain of g, and g of f of x equals x for every x in the domain of f, then they are said to be inverse functions. And here's a little terminology we would use. This, I would read this as f inverse x. Okay, let's build on that. A function is said to be one-to-one if and only if it has an inverse function. A function f is one-to-one for a and b in its domain when the height at a equals the height at b implies that a equals b. Well, interesting. Let's see. Here's the height at a point equals height at another point. But this is height at two different values of the x value. We need that to mean that the only way I can get to a height, let's say I have a height here, the only way I can get to that height, let's say it's up 2, is to be at this exact same value of x. One of the interesting things that happens with inverse functions is going to be explained here. Here's a function, no doubt about it, passes the vertical line everywhere. But because this point and this point are at the same height and they get there through different values of x, it's not one-to-one. Therefore, I think we can quickly see that horizontal line test is a test for one-to-one functions. This one is not one-to-one. Okay, and as I said earlier, existence of an inverse function. Functions have inverses if and only if they are one-to-one. So it's almost synonymous. We have an inverse function. That means the function is one-to-one. Now, in the very most basic terminology, and really this almost answers the question to everything, but it's so simple, it takes a fair amount of understanding and a fair amount of thought process to go through to really get it, but it seems really easy. Inverse functions turn x's into y's and y's into x's. And if you can keep that in mind, things become pretty clear. Let's say, for instance, I have a point 4, 1, and that is my only point on function f. This is f. So f just contains the point 4, 1. If we really understand this, f inverse, well, x's become y's, y's become x's. Here is the graph of f inverse. 1, 4. Okay, so if we understand x's become y's and y's become x's, then that's going to help us out down the road. And you can read through this. It's in your note packet. But this basically says, in the equation for f of x, replace f of x, that's the fancy name for y, with y. Then interchange the roles of x and y. That's because in inverse functions, x's become y's, y's become x's. Okay. Let's take a look at 7 through 14. Find the inverse function of f informally. Well, I'm not exactly sure what they mean informally. Verify that f of f inverse of x is x. Okay, so I'm going to turn this into y. This is a fancy name for y, but I'm going to replace it with x equals 4 times y minus 1. And now I just solve this for y. So that would be y minus 1 equals, divide both sides by 4, x on 4, or y equals x on 4 plus 1. And that is what f inverse of x is. And now we're to show that f of f inverse of x does in fact get us back to x. So let's see. F of f inverse of x is f of x on 4 plus 1. That's f inverse. Well, f is a factory that puts things right here. So this becomes 4 times quantity x on 4 plus 1. Whoops, excuse me, minus 1. Missed that. Minus 1. I'm wrong. Sorry about that again. I just had a distraction here. That becomes, 4 times, in place of x, I'm going to put x on 4 plus 1. This takes the place of x. There's still a minus 1 on there. So that is just 4 times x on 4, and that equals x, and that's what we're hoping for. Now, they do say that we're supposed to then show that f inverse of f of x equals x, and that is because the composition of functions, as we've learned, is not commutative. In other words, 6 times 3 equals 3 times 6, but f of g of x does not equal g of f of x. So we're supposed to show this, but I will tell you, if it works one way as an inverse function and we end up with x, then we're going to be in good shape with that. The second one's going to work as well. Okay, so here I have y equals x to the 7th. I replace y with x. X equals y to the 7th. I solve for y. Y equals the 7th root of x. I check and see if f of f inverse of x equals x. Well, f of f inverse, that would be f of 7th root of x. F is a factor that takes things to the 7th. So quite simply, we get there very quickly. Okay, so x's become y's, y's become x's. Let's look at 15 through 18. 15 through 18, match the graph of the function with the graph. Well, we haven't even talked about graphs of inverse functions yet. Well, sort of we have, because x's become y's and y's become x's. For instance, here is a point 1, 0. The inverse function must contain the point 0, 1. Doesn't contain 0, 1. Whoop, this is A, B, C, D. Doesn't contain 0, 1. Doesn't contain 0, 1. Does contain 0, 1. Doesn't contain 0, 1. Also, this point contains, let's take a look, 1, 2, looks something like, and I don't know the exact values here, but it looks like by the time I'm over to 3, I'm up at about 5. Let's take a look down here. By the time I'm over, so 3 got me to 5, the inverse function should contain 5, 3. 1, 2, 3, 4, 5 gets me up to about 3. Seems pretty good. So I'm going to sketch this graph onto here. So this one goes through here and looks something like, by the time I get to 3, I'm up to 5. Looks something like this. You might notice it appears as though we might have symmetry through here. Okay, B. Here's a graph that has 0, 6 on the function. Therefore, 6, 0 must be on its inverse. Let's see, 6, 0, not on this graph. 6, 0 is on this graph, not on this one, of course, and is on this one. So it must be here. There's 6, 0 becomes 0, 6. There's 0, 6 becomes 6, 0. And once again, it looks as though we would have symmetry over the line y equals x. Let's take a look at C. C is a line passes through negative 1, 0. Negative 1, 0, 0, negative 1. it appears as though it passes through 6, maybe 3.5 or so. 1, 2, 3.5 or so, maybe 6 up here. So this is our inverse function. If I was to sketch this graph on there, it would look something like that. And once again, there's our symmetry. So one thing to note here, this function is increasing. This one is increasing, and so is its inverse. This function is decreasing, and its inverse, while it's itself, is also decreasing. This function is increasing right here. Its inverse is also increasing. Might come as a bit of a surprise. Okay, and of course this one maps with the last one. This one has a point 0, 0. Switch the x and y, 0, 0. This one has the point, appears to be 6 around 2. This one has a point 2, perhaps around 6 up here. If I was to graph the other one on here, it would look something like this. And there's our symmetry line right along y equals x. Y's replace the x's. Okay, let's move on here. Verifying inverse functions algebraically. Now, truthfully, that's what we did back here when it said informally. But verify their inverse functions algebraically. So, first thing we might note, the graph of number 22, 9 minus x squared. Well, if I graph that entire function, hopefully we would know that's upside down x squared up 9. So we're up 9, we pass through 3, we pass through negative 3. That graph really wants to look like this, and that graph is not 1-to-1 and therefore does not have an inverse function. However, it might if we lop off part of it. So they've lopped off the left side of it, and now this function is 1-to-1. Prior to that, it didn't pass the horizontal line test, not 1-to-1. And here could be some informalness, I suppose. Let's say we have 0, 9. We have 0, 9 on this graph, so therefore 9, 0 somewhere out here must be on the inverse. 3, 0 would imply 0, 3. Here's the inverse function of that right there. And we might know what the equation of that is. In fact, that looks like a square root function. Notice decreasing, decreasing. That looks like a square root function, except it's backwards. And the most interesting value of x is 9. So if I did this, that would make the most interesting value of x 9, because that makes underneath the radical 0. Take a look. We're supposed to show this is the inverse function. So I think we're in business here. So all I'm going to do is find f of g of x. So that is 9 minus the thing squared, and I get 9 minus x when I square, and that equals 9 minus 9 plus x, and that is just x. Forgive me here, I'm a little sloppy on taking a look at my screen. I'll get with it. Okay, number 26. In 25 through 34, show that f and g are inverses algebraically. We're going to do algebraically. We can look at it a graph. To do it numerically, we'll take a look at that. So we're going to go here. I'm not necessarily going to graph this. I am going to do it algebraically. So algebraically, we want to take f of g of x. So that is f of 4x plus 9. And we want to show that that is equal to x. F is a factory that puts things right here. So that is 4x plus 9 minus 9 on 4, and we can quickly see that gets us to x. Okay, let's take a look at this numerically. I'm going to clear this one out. Let's go into y equals clear, clear, clear. And let's go ahead and enter that first function, x. Give me just a second here. We've got x minus 9, quantity x minus 9 divided by 4. And we've got, for the second graph, 4x plus 9. I suppose we'll go ahead and take a quick look graphically. I'm going to go ahead and zoom box this, zoom 6. And if I was to go ahead in here and add just y equals x, let's take a look. Does look like there might be some symmetry, especially if I would go zoom square. Might really show that symmetry. Now, for numerically, I'm going to go into my table set. I'm not sure what my table's set at. Yep, I'm just going to set my table set to 0, and I'm going to count by ones. And then I'm going to go to table. And if you take a look, the value, if I put x into the first function, I get -2. If I put 1, into the first function, I get -2. If I put it into the second function, I get 13. Let's jump up here to -2. If I put -2 in the first, I get 1. So x -2, y 1, where it was x1, y -2. If I go down to that 13, if I put in 13, I'm going to expect to get a -2. Let's take a look. I expect to get back to 1. Let me go back up and show that again. 1 got me to 13 on this function, so 13 gets me to 1 on y1. Okay. All right. Let's take a look at 34. This one involves some algebra. I've left some space for this, so I want f of f inverse 2x plus 3 on x minus 1. And we're going to have a little bit of algebra work to do here, and there'll be one like this in your assignment, and you may see another one of these on a quiz or test at some point. So f is a factory that puts things here and here. It's got to put that mess. It doesn't care if it's a mess. It's just going to put it there. So we get the big mess, 2x plus 3 on x minus 1 goes right here. There's a plus 3. All on the big mess, 2x plus 3 on x minus 1 goes here. There's a -2. And at that point, I'm going to go ahead and clean up this mess in one step. You might get common denominators and smash these together, but I'm going to multiply top and bottom by the least common denominator out of this term, this term, this term, and this term. Of course, these have denominators of 1. So I'm going to multiply by x minus 1 on x minus 1, a really important algebra step that makes things much easier down the road. So let's take a close look at this. If I distribute this whole package to this term and this term, when it goes to this term, the x minus 1's cancel and I get 2x plus 3. But when it goes to the 3, it doesn't cancel. So we deliver the whole package to the 3. When I deliver the x minus 1 to this term, the x minus 1's cancel, and I get 2x plus 3. But when I distribute it to the -2, nothing cancels. Now, we're at a dangerous point right now where people may say, well, the 2x cancels the 2x, the 3 cancels the 3, the x minus 1 cancels the x minus 1. We can't cancel any of those. Not a single one of those is a factor of the numerator or the denominator. So we're going to simplify. Let's see, I'm going to do this in one step. I get 2x, I'll get plus 3x, that's 5x. I get a 3 plus a -3, cancels. In the denominator, I get 2x minus a 2x, cancels, and I get 3 minus times minus plus 2, 5, and we've got x. And we have got it. Okay, and 35 to 38, does the function have an inverse? Another way of asking this is it 1 to 1? Those things are basically mathematically synonymous. Is it 1 to 1? If it's 1 to 1, then it's a function, first of all, and all of these are functions. Like a half hour knows what to become. 1 hour becomes $40. 2 hours becomes $70. 4 hours becomes $120. But it has to be a function going backwards as well. That's what an inverse function is. So $1 would become 1 can, $5 would become 6 cans, $9 becomes 12 cans, $16 becomes 24 cans. This is 1 to 1. Is 1 to 1, therefore has an inverse. This function, however, does not have an inverse function. There would be elf confusion getting this 40, knowing what to do with the 40. Does $40 get me half an hour? Does $40 get me half an hour? In other words, if I graph this 1/2 40, and 1/2 would get me 40, and 1 would get me 40, and wouldn't pass the horizontal line test. Not 1 to 1, no inverse. Okay, -3's become 6 all the time, -1's become 5, 0's become 6's, but if I work that backwards, 6's want to become 0 some of the time, and -3 some of the time. So, not 1 to 1, no inverse. 2's become 4's, 3's become 7's, 7's becomes 2's. Work it backwards. 2's become 7's, 7's become 3's, 4's become 2's. 1 to 1, yes, it has an inverse. X's become Y's. Keep that in mind all the time. Okay, in 39 to 44, determine whether the graph is that of a function. If so, determine whether that function is 1 to 1. 39, is it a function? It is not a function, does not pass 1 to 1 line test. Not a function, if you can read that. Number 44, it is a function. However, it is not 1 to 1. Does not pass horizontal line test. 41 appears to be a function. In fact, without a doubt, it is a function. Does it pass the horizontal line test? The only question is right here. What happens right there? And that's a tough one because maybe we need to be able to zoom in on that and look at it closer. I think the author implies, if we find the back of the book answer, I think they imply that this is coming up, just temporarily at one instant pauses and continues up. If that's the case and it only hits that point once, then it has an inverse. Passes vertical line test, passes vertical horizontal line test. Yes, it's a function. Yes, it's 1 to 1. Yes, it has an inverse. Number 43, passes all vertical line tests, passes all horizontal line tests. Yes, it's a function. Yes, it's 1 to 1. Therefore, yes, it does have an inverse. 44 is not a function. As it turns out, its inverse would be a function if we could find the inverse of it, if we could just replace all x's with all y's, and it would actually look something like that, reflection over y equals x. Okay, and number 50, I'm going to split this into two different videos. This is a longer section. In exercise 45 to 56, use a graphing calculator to graph the function and use the horizontal line test to determine whether a function is 1 to 1. So we'll take a look at that. Let's go -2x square root 16 minus x squared. And let's go back to zoom standard. Okay, I think this graph quits on us at points. It looks like around 4, and then we look up at number 50. We say, well, yeah, it makes sense that it might quit at 4 and -4. So all the graph is between there, and clearly it is not 1-to-1. We can see that, but I'm going to go ahead and zoom fit it, which is zoom 8, zoom fit, zoom 0. We can at least see the whole graph. And we can tell, yes, it's a function, but we knew it was a function to begin with. But it does not pass horizontal line test. Therefore, it's not 1-to-1. Okay. I'm going to pause this one at that. There's a second part to this. Apologies, poor start on this video. We'll probably redo it at some point, but hopefully you got the gist of that. So make certain you're asking questions if necessary, and check out part 2.